Hi, in this lesson, I want to introduce you to some of the ideas behind metamorphism. Now, metamorphism is possibly the trickiest of the three groups of geological processes that make rocks, for reasons we'll get into as the lesson continues. But principally, we need to think about how rocks can get changed by a combination of pressure and temperature, and all the implications that has for the textures and the minerals that we find. For this lesson, you're going to need the temperature and pressure graph that's linked to this specification. Okay, let's go. So let's start by thinking about what metamorphism actually is. This is the official definition. Let's try and break that down a little bit. It's defined as a change in either the mineralogy or the texture in a pre-existing rock. So one of the complications of metamorphism is that we're always dealing with rock that used to be something else. And sometimes there are traces or remnants of that pre-existing rock in the metamorphic rock we find. Now these happen because of a combination of heat and pressure. There's also chemically active fluids that can have an effect here. We don't worry about those at all at A level. Crucially, metamorphism does not involve melting. The rocks do not melt because of the heat. This all happens within a solid state. Now the rocks might get soft, they might deform easily, but they do not melt. If they melted, we'd be talking about igneous rocks and igneous processes. It's really, really important to remember that. Now, there are three types of metamorphism that make rock. What we call contact or thermal metamorphism, where the main agent of metamorphism is heat. Regional or burial metamorphism, where we have increasing amounts of heat and pressure as rocks get buried deeper within the crust. And finally, a new type of metamorphism we call dynamic metamorphism or cataclastic metamorphism. This is where there's extreme shear stress applied to a rock. Now for AS level, we don't worry about dynamic. We'll come back to that in year 13. Okay. This graph that you should have on your handout is arguably the most important graph in geology. Because on this graph, we see all geological processes, certainly all rock forming processes. Now, there are different areas in this graph that we need to have a look at. But let's start first of all by excluding some parts of this. You can see on the right hand side there, we've got a partial melting curve. To the right of that melting curve, at higher temperatures than the point where melting starts, that's where we have igneous rocks. So the red area on this graph represents igneous processes. So for this lesson, we're not really interested. Similarly, at the far top left of this graph, we've got conditions of very low temperature and pressure that I've shaded in blue on this graph, and they represent sedimentary processes. At the surface to erode, transport and deposit, and then at shallow depths and relatively low temperatures to lithify those sediments. There's another area on this graph on the left. It's labelled up as the limit of metamorphism. Now in this area that I've shaded grey, we have no rocks being formed. These conditions don't naturally occur on Earth. We can't have pressures to that extent at such low temperatures. So that grey area doesn't exist. What we're left with in the middle, this wide range of temperatures and pressures between sedimentary and igneous processes, is where metamorphism occurs. And this is the second reason why metamorphic rocks can be tricky, because there's such a wide range of pressures and temperatures at which they'll form. Now you can see that there are two areas labelled up here. Contact metamorphism, which has low pressures and increasingly high temperatures, and regional metamorphism then, which has higher pressures and high temperatures as well. And you can see that there's a progressive line of different types of metamorphic rocks for us to consider. Let's look at this in a little more detail. On the left-hand side here, we've got relatively low pressures and temperatures. This is what we describe as a low-grade metamorphism. Now, for us at A level, that's represented by a rock called slate. Phyllite isn't one of the ones we need to know. You can cross that out on your graph. When temperature and pressure increases, which will happen proportionally if the rock's being buried within the crust, we then see a medium grade of metamorphism, represented by the metamorphic rock schist. The final area here, represented by gneiss, at the higher temperatures and the higher pressures, those are our high grade metamorphic rocks. So clearly, temperature and pressure has a major effect on the types of rocks that are produced. To summarise, increasing temperature, increasing pressure lead to a higher metamorphic grade. Okay. Now these different types of metamorphism are related to the causes of this heat and pressure. For contact metamorphism, this is where we have metamorphism, very localized metamorphism, around large igneous intrusions and the country rock. The heat is from the intrusion, from the magma, and that has most effect. The highest grade will be immediately next to the igneous rock. The further away we go, the lower the grade of metamorphism, the less rock has been metamorphosed, until we reach a point where the metamorphism stops. Fluids can be important. We're not going to worry about those too much. To try and illustrate this, we think about this feature we call the metamorphic aureole. Now, there's more detail of this in the homework task on contact metamorphism. But this area surrounding the pluton, we'll see high grade close to the contact and progressively lower grade further away. It's a key feature really of all aureoles. So when we think about contact metamorphism then, we need to think carefully about the temperature of the magma. Mafic magma is hotter than silicic magma, for example. The temperature of the country rock. We get most metamorphism where there's the biggest contrast between the magma and the country rock. How conductive to heat the magma and the country rock are. What's the temperature of that the magma crystallizes at? As I said, fluids can have an effect as well. And there may be other sources of heat as well, particularly at depth. Regional metamorphism, then, is controlled really by its position within the crust. And we can find different types of metamorphism depending on, firstly, how deeply the rock is buried. So, for example, if we have rock deposited to a relatively shallow depth, maybe 3, 4, 5 kilometers down, we'll have relatively low temperatures and relatively low pressures for metamorphism. The deeper that rock goes, the higher the temperature becomes, the higher the pressure becomes. And we'll see from that our progression as we go from slate through schist through gneiss. Each of those represents a different stage of metamorphism. Now, there are some unusual types of regional metamorphism, particularly associated with plate boundaries, where we can get higher pressures with lower temperatures, with the pressure coming from the compression caused by the plate movement. We can get a specialist type of rock that's relatively unusual called blue schist in those type of environments. So, as the sun sets on the Callanish stones, all made of Lewisian gneiss in the Outer Hebrides, we can see from this that temperature and pressure and the interaction of the two are key to understanding metamorphism, both the type of metamorphism and the grade of metamorphism that occurs. What we as geologists need to be able to do is to recognise how the rocks that we see relate to the pressure and temperature conditions at which they form. We need to have a look at a bit more detail then at the minerals that would be found at these different stages of metamorphism, but that's for another lesson. I'll see you then.